Statistical Multipath Channel Models. In this section, we will be studying, this is the syllabus. In this section, we will be studying about time varying channel impulse response, narrow band fading, wide band fading, delay spread and coherence bandwidth, Doppler spread and coherence time, flat fading versus frequency selective fading, slow fading versus fast fading, and discrete time model. Second module 2.2. What is time varying channel impulse response? The small scale variations of a mobile radio signal can be directly related to the impulse response of the mobile radio channel. The impulse response is a wideband channel characterization and contains all information necessary to simulate or analyze any type of radio transmission through the channel. So, in this what we are going to see is that we are going to see the response of the system when we give an impulse signal to the system. This is called as a channel model. We are trying to find out what are the possible characteristics that's going to work out with this particular channel if we are giving an impulse signal as an input. Some important consideration or factors that is going to affect the wireless channel. First one is the time delay spread, time varying nature, the received power in terms of dB. The received power PR is given by the sum of the transmitted power plus the path loss plus the shadowing plus the power due to multipath. So all these things will reduce the total power that is being transmitted, and finally you will have a received power. So what is that is going to really affect the received power is the path loss, shadowing and multipath. Another one important feature is about Doppler shift. See, in this particular wireless communication, we have something called as mobility management. I'm not sure whether I've told you about this before. There could be a chance that, or there is a chance that the receiver is moving. The receiver could move faster. As the receiver moves faster from the transmitter, the distance between the transmitter and the receiver is increasing, and naturally from the previous class I think that you will understand that the power at the receiver end is getting reduced. The power at the receiver will get reduced because of the shift. The distance is increasing. Doppler shift will create another reduction in the power. So we have to consider all these factors while we design a channel. First thing what we'll be doing in this particular class is about analyzing what happens if we give an impulse signal as an input to a wireless channel. The wireless channel which is time varying. That means the characteristics of the channel varies with the increase in time or with the change in time. Now let us consider a transmitted signal S of t. S of t will be the real part of u of t e raised to j 2 pi fct. That means u of t is the low pass signal for S of t with the bandwidth b, and fc is its carrier frequency. The received signal is the sum of the line of sight path and all resolvable multipath component not considering the noise, and that would be given as R of t. Now this is the signal transmitted. Says transmitted signal is S of t. It is mathematically given here, and the received signal R of t is given with respect to U of t, the equivalent low pass signal for S of t. Okay, here you can see that we are considering only the real part, that is only the magnitude and not the phase. Is that clear? Write down what is about for the transmitted signal S and the mathematical model for the transmitted signal S of t and the received signal R of t. So R of t is given by the real part of sigma n is equal to 0 to n of t, an u of t minus tau n of t e raised to j 2 pi fc t minus tau n of t plus phi dn. Okay, that is n of t is the number of resolvable multipath components, the path length r of Rn of t, and the corresponding delay. Now tau n of t is given by Rn of t by c, Doppler phase shift. As the receiver moves, we'll have a Doppler phase shift which is called as phi n, and the amplitude an, the observation time t at the receiver. We'll be considering this. In this case, whenever we are going for the derivation, the time at the receiver is considered as t, and t minus tau, or the time at which it is being, the signal, impulse signal is being launched, is considered to be t minus tau. Okay. Resolvability criteria for multipath components. You have multiple paths. See, tau 1 and tau 2 are the time taken for the signal to reach the destination in two different paths. Tau 1 and tau 2 modulus should be greater than du inverse. This is called as the resolvability criteria for multipath components. If u of t minus tau 1, that is the transmitted signal, u, we have already defined S of t, right, in terms of u. I believe that all of you remember that if u of t is t minus tau 1 is approximately equal to u of t minus tau 2. That means the time at which both the transmission is happening now, the signal is transmitted at the same time from one point, approximately the same time, then they are unresolvable. Okay. These unresolvable components are combined into a single multipath component with time delay, which is called as tau, which is approximately equal to all the different transmission times. Is that clear? So let us consider this to be a transmitter and this to be a receiver. You have multiple paths. Let us take this to be tau 1, this to be tau 2, there will be a difference in time when the signals are transmitted at approximately the same time and received approximately at the same time. That is t minus tau 1 and t minus tau 2 are approximately equal, then these signals are unresolvable. So in general, wideband channels have resolvable multipath components. Now we are going to see how we are going to resolve these multipath components, so that each term is in the summation in the equation corresponds to a single reflection or multiple non-resolvable components combined together. Whereas narrowband channels tend to have non-resolvable multipath components contributing to each term in the equation. Delay and Doppler. Phi n of t is equal to 2 pi fc tau n of t minus phi dn, where phi dn is the Doppler effect. This change in phase shift due to Doppler effect. In that case, what will happen to the received signal R of t? R of t will be equal to the real part of sigma n is equal to 0, n of t. What is n of t? The number of resolvable multipath components. Alpha n e raised to minus j phi n of t u of t minus tau n of t e raised to j 2 pi fct. The received signal R of t is obtained by convolving the equivalent low pass input signal u of t with the equivalent low pass time varying channel impulse response, which we are going to denote by C, tau and t. C, which is a function of the channel impulse response, C, which is the function of t and tau of the channel, and then converting to the carrier frequency. R of t is then given by the real part of minus infinity to infinity, the channel response Ct of tau comma t, the function of both tau and t. U of t minus tau d tau e raised to j 2 pi fct. Low pass frequency response of the channel at time t, the time observed or the time at which it is received, to an impulse at the time t minus tau, time when the impulse is put into the channel, is given by C, which is a function of t, and tau is equal to 0, sigma n is equal to 0 to n of t, alpha n e raised to minus j phi n of t delta, impulse function delta t minus tau n of t. Substituting in the receiver equation R of t, we are substituting the value of C tau of t. We'll get the real part of minus infinity to infinity, n is equal to 0 to n of t. Here we are substituting the value for C of tau comma t. And while then we are solving this equation to get the signal that is being received at the receiver. Some channel models assume a continuum of multipath delays, in which case sigma n is equal to 0 n of t alpha n e raised to minus j phi n of t delta t minus tau n of t becomes an integral that simplifies into a time varying complex amplitude associated with each multipath delay. In that case, we would be getting the impulse response Ct of t, C of tau and t equal to integral alpha eta comma t. Alpha as a function of eta and t e raised to minus j phi of eta comma t delta t minus eta d eta, which is equal to alpha tau comma t. Alpha function of tau and t e raised to minus j phi tau minus t, where eta is defined as 10 by natural log of 10. So in this you can see that the transmitter and the receiver, you can see that there is a vehicle. We are using a multipath system, and tau represents the time taken for each signal to travel from the transmitter to the receiver. We'll be having as many number of resolvable paths, so much values for tau. Okay. Here this is for the two-ray model. Actually there is only one tau. At time t1, there are three multipath components as shown in the figure associated with the received signal and with the amplitude, phase and delay triple. We have three components alpha I, phi I and ti. Okay, I is equal to 1, 2, 3 and the I denotes the different paths adopted by the signal, multipath signal. The time varying impulse response corresponding to T1 is given by C tau T1 is equal to sigma n is equal to 0 to 2. We are considering three multipath components alpha n e raised to minus j phi n delta tau minus tau n. Consider the second point at time 2 t2. There are two multipath components associated with the received signal and with the amplitude, phase and delay triple alpha dash I, phi dash I, t dash I, same I is equal to 1 comma 2 comma 3. We are giving three values. The time varying impulse response corresponding to time t2 is equal to C function of tau and t2, that is equal to sigma n is equal to 0 to 1 alpha n e raised to minus j phi dash n delta tau minus tau n.